Hello everyone and welcome back. In the last video we talked about the linearization of a function, which is approximating the function by using its tangent line at a point. In this video we're going to talk about extending this idea of approximating functions by using polynomials. And these approximations are called Taylor polynomials. These are named after the English mathematician Brooke Taylor, who introduced the idea back in the 1700s. Now let's consider the linearization of the cosine of x at a equals 0. So to find the linearization, we need to determine f of 0 and f prime of 0. So f of 0 is the cosine of 0, which equals 1, and the derivative is the negative sine of x. And so f prime of 0 is negative sine of 0, which is 0. And so if we use these values, we obtain the linearization, which is 1 plus 0 times x, which simplifies to 1. So now let's suppose that we want to find approximations of cosine near 0. For example, let's approximate the cosine of 0.25. Now if we use the linearization, we know that f of 0.25 is the cosine of 0.25, so that means we evaluate the linearization at x equals 0.25. But if we evaluate L of x at 0.25, we end up with 1. This tells us that the approximations near 0 will always be equal to 1, which, although is true, it isn't very helpful for this case. But rather than using a linear function to approximate the cosine of x, let's try using a quadratic function instead. And so this quadratic function is called the second degree Taylor polynomial, centered at x equals a, and is given by this formula here. So the second degree is f of a plus f prime of a times x minus a, plus the second derivative of a over 2 factorial times x minus a squared. So notice that this is similar to the linearization. So we have the f of a plus f prime of a times x minus a, but we have this additional quadratic term. So if we look at the second degree Taylor polynomial, which is given by this blue curve, we see that it fits quite closely to the cosine of x when x is near 0. And so we can use this second degree Taylor polynomial to get a better approximation for the cos of 0.25. So let's find the second degree Taylor polynomial for the cos of x centered at 0, and we'll use it to approximate the cos of 0.25. So the second degree, given by f of 0 plus f prime of 0 times x minus 0 plus f double prime of 0 over 2 factorial times x minus 0 squared. So what we need is to determine f of 0, f prime of 0, and f double prime of 0. So for the cosine function, we know that its first derivative is negative sine, and the second derivative is negative cosine. So now we can determine f of 0, which is cos of 0, which equals 1. We can determine f prime of 0, which is negative sine of 0, which is 0. And f double prime of 0 is negative cos of 0, which is negative 1. And so the second degree Taylor polynomial is 1 plus 0 times x plus negative 1 over 2 factorial, which is 2 times 1, times x squared. And so simplifying, we end up with 1 minus 1/2 x squared. So now let's approximate cosine of 0.25. We know that f of 0.25 is cos 0.25. And so we can approximate this using the second degree Taylor polynomial evaluated at 0.25. So 1 minus 1/2 times 0.25 squared, which will give us 0.967875. So why stop at a quadratic function to approximate f of x? What if we used a higher degree polynomial instead? Well, we can extend our approximations to any degree that we wish. And so the nth degree Taylor polynomial is given by this formula. So in the general form, it is f of a plus f prime of a over 1 factorial times x minus a plus f double prime of a over 2 factorial times x minus a squared. And we continue in this pattern until we end up with the nth degree of f evaluated at a over n factorial times x minus a to the power of n. So the graphs below show the 4th and the 6th degree Taylor polynomials for the cosine of x. Notice that as we use a higher degree Taylor polynomial, then the approximations near 0 becomes more valid in a larger interval. And so the higher the degree, the more approximations we can make that are further from 0. So now let's look at some examples for calculating these Taylor polynomials. Let's find the 4th degree Taylor polynomials centered at 0 for each of the following functions. So the 4th degree Taylor polynomial centered at 0 is given by f of 0 plus f prime of 0 times x minus 0 plus f double prime of 0 over 2 factorial times x minus 0 squared plus f triple prime of 0 over 3 factorial times x minus 0 cubed plus the 4th derivative of 0 over 4 factorial times x minus 0 to the power of 4. So now let's find the 4th degree Taylor polynomials for hyperbolic sine. So in order to find the 4th degree Taylor polynomials, we need to find f of 0, f prime of 0, f double prime of 0, f triple prime of 0, and the 4th derivative evaluated at 0. So we need the 4 derivatives, or the 4th derivative of the hyperbolic sine function. Well, we know that f prime is cosh, f double prime is sinh, and f triple prime is cosh, and the 4th derivative goes back to sinh. So now let's evaluate these functions at 0. So f of 0 is the sinh of 0, which is 0. F prime of 0 is the cosh of 0, which is 1. F double prime of 0 is sinh of 0, which is 0. The 3rd derivative at 0 is cosh of 0, which is 1. And the fourth derivative of 0 is sinh of 0, which is 0. So now we can find the fourth degree Taylor polynomial. So we have 0 plus 1 times x plus 0 over 2 times x squared plus 1 over 3 factorial, which is 6 times x cubed, plus 0 over 4 factorial, which is 24 times x to the 4. And so simplifying, we end up with x plus 1/6 x cubed as our Taylor polynomial. So now let's find the fourth degree Taylor polynomial for the ln of 1 plus x. So we need the fourth derivative. So f prime is 1 over 1 plus x. And by the chain rule, we multiply by the derivative of 1 plus x, which is 1. And we can rewrite this as 1 plus x to the negative 1. The second derivative is negative 1 times 1 plus x to the negative 2. The third derivative is 2 times 1 plus x to the negative 3. And the fourth derivative is negative 6 times 1 plus x to the negative 4. So now let's evaluate all of these functions at 0. So f of 0 is the ln of 1, which is equal to 0. F prime of 0 is 1 plus 0 to the negative 1, which equals 1. F double prime of 0 is negative 1 times 1 plus 0 to the negative 2, which is negative 1. F triple prime of 0 is 2 times 1 plus 0 to the negative 3, which equals 2. And the fourth derivative of 0 is negative 6 times 1 plus 0 to the negative 4, which equals negative 6. And so the fourth degree Taylor polynomial is equal to 0 plus 1 times x minus 1 over 2 factorial, which is 2, times x squared, plus 2 over 3 factorial, which is 6 times x cubed, minus 6 over 4 factorial, which is 24, times x to the power of 4. And so simplifying, we end up with x minus 1/2 x squared plus 1/3 times x cubed minus 1 over 4 times x to the power of 4. And you might notice a pattern in the coefficients for the Taylor polynomial. So what would the fifth degree Taylor polynomial look like? Well, if we wanted to find the fifth degree Taylor polynomial, this would be x minus 1/2 x squared plus 1/3 x cubed minus 1/4 x to the power of 4 plus 1/5 x to the power of 5. So now let's find the fourth degree Taylor polynomial for 1 over 1 minus x. So we can rewrite this as 1 minus x to the power of negative 1. So we need to find the fourth derivative. So the first derivative is negative 1 times 1 minus x to the power of negative 2. And by the chain rule, we multiply by the derivative of 1 minus x, which is negative 1. And this can be simplified to 1 minus x to the power of negative 2. Now the second derivative is negative 2 times 1 minus x to the negative 3 multiplied by negative 1, which can simplify to 2 times 1 minus x to the negative 3. The third derivative is 2 times negative 3, which is negative 6, times 1 minus x to the negative 4 times negative 1, which is 6 times 1 minus x to the negative 4. And the fourth derivative is 6 times negative 4, that's negative 24, times 1 minus x to the negative 5 times negative 1, which is 24 times 1 minus x to the negative 5. And so now let's evaluate each of these functions at 0. So f of 0 is 1 minus 0 to the negative 1. So that's 1 to the negative 1, which is 1. F prime of 0 is 1 minus 0 to the negative 2. So 1 to the negative 2, which is also 1. F double prime of 0 is 2 times 1 minus 0 to the negative 3, which is 2 times 1 to the negative 3, which is 2. The third derivative at 0 is 6 times 1 minus 0 to the negative 4, which will simplify to 6. And the fourth derivative, evaluated at 0, is 24 times 1 minus 0 to the negative 5, which will simplify to 24. And so the fourth degree Taylor polynomial is going to be 1 plus x plus 2 over 2 factorial, which is 2, times x squared, plus 6 over 3 factorial, which is 6, times x cubed, plus 24 over 4 factorial, which is 24, times x to the 4. And simplifying, we end up with 1 plus x squared plus x to the 3 plus x to the 4. And again, you can see a pattern with the Taylor polynomial. If we wanted the fifth degree Taylor polynomial, we would just add the term x to the power of 5. And so this concludes our lesson for this video. In the next video, we'll start the next chapter, which is on applications of differentiation. And I'll see you then.